Okay, so back page, Unit 5, Chemical Formulas. A few things just kind of keep in mind about this. Chemical formula just shows you the simplest form of a chemical compound. Okay, so it's all about compounds of some kind. It's not spelled like that. We talked about the fact that chiefly there's two main kinds of chemical compounds that have different rules for formulas. You've got ionic, which is chiefly between a metal and a nonmetal ion, where the metals end up losing electrons to the nonmetals, which means that your metals are going to take on a positive charge. Your nonmetals are going to take on a negative charge, and that's going to be what ends up attracting them to each other. Okay? When you have an ionic compound, the formula needs to show a balance of charges. Okay? In other words, you need to make sure that all your positives and negatives are equal by writing however many of these positive ions you have over here and how many of these negative ions you have over here. Okay? You're always going to have positive piece, negative piece. Okay? Cation, anion. Even if it looks like there's more than two things there, even if I've got something goofy like H2SO4, I got two pieces. Positive piece, my hydrogen. Negative piece is my SO4, because that's a polyatomic, right? Okay, Muppet Man. When you're doing stuff with ionic, a really helpful tool for that is your blue chart. Okay? Your oxidation chart, your ions. That will help you with names. That will help you with the charges of your positives and the charges of your negatives. Okay? On the other hand, the other kind of compounds are your covalent compounds. Covalent compounds are going to be between nonmetals. And in a covalent compound, you don't have a positive piece or a negative piece. You just have nonmetals that are sharing electrons in between. Sometimes they're sharing one pair, sometimes they're sharing two or three. When you're looking at the formulas, you don't have to worry quite so much about how many pairs they're sharing. All you have to worry about when you're looking at your covalent formulas and names of those formulas are your prefixes. The prefixes tell you how many of each piece you have. Okay? If there's only one of something, the prefix is mono. Okay? If there's two, what is it? Di. There's three, tri. 4 is tetra. 5 is penta, and so on. Okay? And so all you have to worry about, if I've got like diphosphorus trifluoride, you look at your prefixes. Di here means 2, so for my phosphorus, I'm going to have 2. Tri means 3. So it's just like that. Covalent's a lot easier as long as you know what you're looking for. Okay. You're still going to have 2 pieces. You're not going to have positive piece, negative piece. You're going to have slightly weaker and slightly stronger, usually. Okay. So if I've got, my strongest elements are going to be the ones that are up toward the top right, like my fluorine, my oxygen, my chlorine. And so they're going to be the stronger, slightly more negative piece. The weaker, slightly more positive piece is going to be here. But it's not a true positive and a true negative because nobody's stealing electrons from anybody. Nobody's becoming ions. Let me see. Anything else about formulas on there that you need to know or have questions about less? Anybody else? Okay. Remember all that? So what? How to do it? Yeah, anything that is a reference like that you've been collecting, you are welcome to use on the test. Okay. Any other questions? Okay. All right. What would you like to talk about next? No wrong answers. So what I can do is I can pause this and go a little bit of time to look through stuff, and if you come to something like I have to move that looks over, then yes. So what? We haven't talked about it yet. Would you like to? Okay. What out of that is main thing you'd like to catch? The 4 rules? Okay, sure. Okay, we can do that. Okay, so the rules for electrons. Okay. Things to keep in mind, our picture of the electron has changed over the years since we first discovered it back with Thomson's experiment up until our most recent understanding. We do know that electrons are very tiny, they have a negative charge, they move around very, very erratically, and they're very, very spooky in the way that they move. 4 rules that we discussed having to do with how they move the way they move and how we can predict where they're going to be. That all has to do with a branch of chemistry called quantum mechanics or quantum physics. And that is all about making predictions of where these electrons are going to be. It's all about probability. Okay? I mean, I could have the nucleus of an atom right here, okay? And the electron could literally be anywhere. I could have it right here. Its electron could be in Wisconsin. Probably won't be, but it could be. There are certain places where it's likely to be found, okay? While it could be anywhere from here to the radius of the atom, it is likely to be found at certain distances, okay? Maybe right here, or maybe right here, or maybe right here, okay? And those are the places where it's going to be the most stable. Okay? We call those regions of space around an atom orbitals. Okay? And those orbitals are found at different energy levels. So, talking about the rules that helped us understand all this, first big one has to do with what's called the Heisenberg uncertainty principle. I probably spelled that wrong. Heisenberg says that you can't know an electron's position and velocity at the same time. If we know where an electron is at a moment in time, we can't know where it's going. If we kind of have an idea of what direction it's going and how fast and stuff like that, we can't know where it is. Okay? Which is part of the whole thing about it being about probability. A guy named Aufbau came along with the Aufbau principle. And he says that electrons will get as close to a nucleus as they can, because that's where they're the most stable. So, if here's the nucleus, if an electron had to choose between position A, position B, or position C, where does it want to be? It wants to be at A. It wants to be as close as possible. Now, what if there's already electrons there? Then it's going to go to the next one up. Exactly. Okay? It's going to get as close as it can without other electrons pushing it away. I talked about the Aufbau principle. I called it the glass of water principle, because water, when you fill the glass, is going to fill the bottom first. And if there's already water there and I add more water, it's going to fill slightly higher. It's going to try and get as close to the Earth as possible, because gravity's pulling it in. Here, the positive protons in that nucleus are pulling it in. Same kind of thing. The third one was the Pauli exclusion principle. What Pauli said is that no two electrons can occupy the same region of space and have the same velocity in an atom at the same time. Okay? Because, just like two people can't occupy the same space at the same time. Okay? If you try and walk through somebody, it doesn't work, right? You all bump and fall down. Okay? Same thing with the electrons. So electrons can share an orbital if they have what's called opposite spin. In other words, if I depict an orbital like a box, and I'm going to use my arrows to notate those electrons, two electrons can go into this orbital provided that one of them has what's called a positive spin and the other one has what's called a negative spin. We represent those as arrows going two different directions. You can't have two up arrows in the same box. Okay? I can't have two electrons. If two electrons are sharing this particular orbital right here, I can't have them both go in the same way because they're going to crash into each other. So magnetically, one's going to be charged one way, one's going to be charged the other way. We say that their charge is either positive or negative 1/2. 1/2 what? Excuse me, I don't know. And the fourth one, I can extend this just a smidge. Whoa! The fourth one is Hund's rule. Hund said, well, if you've got, let's say, 3 orbitals that are at the same energy level, let's say that these are all 2p, okay? That when electrons try and fill in that orbital, since these are all 3 kind of technically the same distance from the nucleus, if the first electron goes into this orbital, then if another electron is added, it's not going to share that same orbital. It's going to go on to the next one. And if a third one comes in, it's not going to share either of those. It's going to go on to the next one. Because that way they're all equally close. They're just kind of equally close in different directions. Before another one comes in and you have like the electron number 4, electron number 5, and so on. I talked about it's kind of like guys in the bathroom. Okay, they're going to all want to go to the bathroom, same bathroom if they have to, but they're not going to want to get too close together. Okay, because they repel. That's the 4 rules. So questions there? If no, what do you want to talk about next? Doing great on time. Where's Steve? I can pause it until you guys come to something you got questions about.
Would you like possibly work out an ionic problem?
Totally. Ionic problem, like, I don't need to name one or write one?
Like put one up there and then like work.
So name one or write one?
Name one.
Okay, sure. Okay, sure. Let's see. Okay. Well, that's definitely ionic because I've got a metal right here. I've got a polyatomic nonmetal ion right here. So I'm going to consult my blue chart. I'm going to first of all look to see what the name of my metal is. I find he's calcium. I look on my blue chart to see where he is, and I find that the only place he shows up is in the +2. Okay, he does not have no Roman numerals, so there's no little 1 or no little 2 or no little 4 or any of that jazz. So I know his charge is going to be +2. I don't have to go hunt for it. PO4, I go to look up PO4 on the negative side of my chart. And I find that PO4 is phosphate. Now, since I didn't need to find out what calcium's charge was, since it can only be +2, I don't have to say calcium 2 phosphate. I just say the name is calcium phosphate. So you keep your fingers crossed that it's going to be daddy.
And don't you do the like swapping?
That's only if I'm writing the formula. See, I've already been given the formula, I just need to find the name. Okay. Now, if I'm given something more like this, that's also going to be ionic because I've got a metal and I've got a nonmetal. So I find my metal. What is Fe? That's iron. Iron could be multiple. It could be +2 or it could be +3. And so since I don't know which one it is, I then go look to see what it's bonded to. It's bonded to a sulfur. When sulfur is by itself, it's called sulfide. It is -2. So if this is -2, it's only hooked up to one iron atom, so this iron has to be which one? So since it has to be that, I use that in the name. So it's iron 2 sulfide. Okay. Usually writing the names is a little bit easier than writing the formulas. I have to write the formulas from the names. That can be a little bit trickier. So let's say that I've got like manganese 5 oxide. Here, I have to figure out the charges. Now, they're nice enough here to tell me what the charge of manganese is. What is it? Uh-huh. Mn has a charge of +5. Oxide is just an O with a -2. Is there not a manganese 5?
No.
Okay, well, I'm just making it up for an example. Okay, that's fine. You sure there's not an Mn5? It's right there, dude. No, it's totally not there. Okay. Well, I hit the one it couldn't possibly be. So, all right. You want me to make it 6?
Yes.
That's fine. I'll give the people what they want. Okay. Fine. Okay. Manganese 6 oxide. So, they're nice enough to tell me what the charge of manganese is going to be right here. Give me +6. So now, since these two charges are not the same, okay, I got to figure out how many of each I'm going to need. I can do the crossing over trick, but I got to be careful with the crossing over trick here, because if I do the crossing over trick and cross that down there and cross that down there, then I end up with Mn2O6, and that's wrong. No. I can reduce the ratio of 2 to 6 into 1 and 3. So it would just be Mn03, Mn1O3. Okay. Now, if they don't give you the charge, you gotta go look it up. Okay? But it's the same kind of deal. We are just about out of time, so y'all go ahead and get your stuff together. Please come to me tomorrow with more questions, so I got something to talk about. See you then.